Beautiful, welcome back guys. It's been a hot minute. I've had a bit of uni delays and there's also been, I used the wrong formula, so we're sort of re-recording this. It's a bit of a journey, but hopefully this gets to you guys not too late into term 4 while you guys are all studying up for the finals. We'll be covering merge sort today. So merge sort is a key knowledge part of the curriculum, so you're gonna have to know this one. And it's what I refer to as an advanced sorting algorithm. So unlike your previous like insertion sort or bubble sort, which are O(n) squared, this is an n log n sort. The reason it's like this is because it uses some of those advanced programming techniques you guys have learnt about, specifically divide and conquer here today. If you're looking for pseudocode for it, typically you'll find it recursive, but I always prefer things iteratively, and I guarantee you can find a good iterative implementation. I've got one as well I'll provide to you guys. The last key piece of information here is that it actually uses O(n) data. So that will come in more when I compare it to Quicksort, which Callie hopefully covered, and you hopefully have watched that video. But that is one drawback, is that unlike the other, what we refer to as in-place sorting algorithms, this has to create its own data. So how does it work? So it's going to create these subarrays by splitting your original list by half each time until they're size 1 or it can't be divided anymore. Now, the real trick and the real reason that merge sort works is because subarrays are sorted by definition. So what that means is when you're combining subarrays, you're not actually doing a sorting. Instead, you're doing a binary insertion, which isn't as expensive computational mechanic. So when all subarrays are combined, you will have a sorted list at the end. Now here's two pieces of code. On the left or right, one side for you guys, there's a recursive version. There's also an iterative version I put on the other side. Again, nice to recognize both these. I know it's not raw pseudocode, but hopefully at this point in the course, you guys can convert Python between pseudocode. Okay, time complexity. This is the big thing. So we consider splitting to be a constant time event, and inserting into a sorted list, as you guys know, is an O(n) event. So we can think of this as inserting all elements of one sorted list into another. Now there is a lot of recursive functions you can do, and I recommend, maybe as a bit of a step away, get this recurrence relationship, but I'll give you the sort of final answer, and it's 2 times time of n divided by 2 plus O of n. So Tn is obviously the time takes to sort the algorithm, that's the total cost. The first term is just referring to the total cost is 2 times each half, which sort of makes sense, and On represents the time it takes to sort said merged halves. Now, this is the part I have to re-record because I used the wrong thing. I used logs. Master theorem is now using powers instead of logs. I'd really recommend making sure you can brush up on both of them, but I think honestly powers are probably more intuitive for you guys. So let's talk about how we can figure out its time complexity from the recurrence relation using the master theorem. Now, luckily we already have it in the layout of the master theorem. We have it as a times t n divided by b plus a function of n. So for our case here, it's obviously t n 2 times n divided by 2 plus O of n. And that can be broken down to a is 2, it's that first value, b is 2, it's the value the n's divided by, and f is O of n to the power of c. In our case, c is 1 because O of n to the power of 1 is O of n. Now, it's a pretty simple step. You just have to compare a and figure out if it's greater than, equal to, or less than b to the power of c. And those are your 3 rules for the master theorem. I haven't included a picture of here because you guys, I know you will get it provided in your exam, but I'd recommend at least knowing each of the 3 conditions. Don't have to really realize what they actually output is, as you'll have that in the exam, but understanding 3 conditions is pretty important. Now, obviously here, we've got 2, and b to the power of 1 is 2, because b is 2. So we have a equals b. So that falls under the second case of the master theorem, making it O n log n. This is just a last little bit of comparison. I don't know if you will get tasked on this in the final exam, but I think it's just good knowledge to have inherently. Now, Quicksort doesn't need space. That is one big upside for Quicksort, because both these algorithms have a best case sort of expected case of n log n. A big difference though is Quicksort is actually worst case n squared, whereas merge sort is worst case n log n. So if you're pure speed, you don't have to worry about anything to do with space inside your computer. Technically, merge sort is better. Merge sort works without randomly accessing data, so it can work in a linked list, unlike Quicksort, which has to randomly pick a point of the data. and merge sort uses more memory if it can be internal. Now you guys don't have to worry about memory handling, it is just a reference, but I think the two key points you should remember is that quicksort is worst case n squared, and merge sort requires memory. Beautiful. Thanks for watching, guys. I understand this was a very dry video. There's no storyline here. Merge sort and the other sorting algorithms can be quite dull. Hopefully when we get back to other topics, we find them a little more interesting. But obviously, if you have any questions, check the LMS. Make sure you understand merge sort, quicksort, how these advanced programming techniques help figure out these sorting algorithms, and refresh yourself on the master theorem for me. Beautiful. Lovely seeing you guys.